afternoon. Thank you for coming to our first Hantel Tech Webinar Series lecture of 2011. My name is Julie Choi, and I'm part of the engineering team, and we want to welcome both our on-site and our virtual attendees to this meeting. Thanks for joining us. So in this forum, we discuss diverse topics related to medical device development, and we'll open to the format. The first initial part will be the lecture, and we'll open the last 10 minutes or so to questions for the floor. And if you're a virtual attendee, please enter your questions in to the chat box, and we'll relay your questions aloud to the speaker and also the live audience. So as the first speaker, I've known Louis Malito since he was a dedicated undergrad interested in research in the Department of Biomedical Engineering at UC Davis. And as far as I can remember, he's been enthusiastic about the machine shop and also medical devices, particularly stents. And he's worked in production at Nitinol Devices and Components, NDC, and has recently joined a startup partner with NDC, which is in R&D engineering called Biomedical. And today he'll share about a topic close to his heart, and the use of Nitinol in medical devices. So without further ado, we'll hear what we have to share from today.
Oh, for clicking the slides. Oh, okay. 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 So, as Julie said, my name is Louis Malito. To give you a little bit perspective about my background, I went to UC Davis and graduated with a Bachelor's of Science in Biomedical Engineering, an emphasis in medical device development. What that basically boiled down to is I took a plethora of mechanical design classes and had a lot of experience in the machine shop, just doing hands-on tinkering and building things. How I kind of got interested more in medical devices is I was always fascinated with engineering and maybe applying engineering to the human body, and medical devices and studying biomedical engineering was kind of like the perfect fit for that. So how I got introduced to Nitinol was actually through a senior design project. So every engineering senior graduate at UC Davis has to go through 2 quarters of a design project. So they take a concept from start to finish and try and build a prototype from it. And so I was partnered with a veterinary interventional radiologist at the UC Davis med school, and he had an idea of solving a problem found in dogs called pericardial effusion. Basically, you had fluid buildup around the pericardial sac of the heart, and he said, well, I put stents in dogs as they are now. Why couldn't a team of undergrads come up with an idea of making a Nitinol stent or a stent in general to open a hole in the heart and drain the fluid to alleviate the pressure on the heart for the dogs and give them a little bit better life. And so that's how I got started with working with Nitinol and stent design, and lucky enough through the project I was able to have NDC sponsor it and make several prototypes that our team of undergrads got to play around with. As you can see pictured here, this is it's a pretty crude stent to what I'm used to now working in the medical device field, but this was our first stent that we came up with to try and solve this problem. And it's got hooks to kind of anchor the stent into the pericardium. It's got a ring of struts around here to kind of force the pericardium open, and we have extra rings of struts to prevent the stent from jumping out of the catheter. But as crude as this stent was, it was my first and our team's first real venture into Nitinol and medical devices. And as you can see on the next slide, we worked really hard to test our device, and given being in ag school and having a low budget, we were able to go to the butcher and get some pig pericardium and string it up around a box and try and test the radial outward force of our stent. So, but this all culminated finally with my graduation and an offer from NDC to work there as an intern, and that was kind of my first foray with NDC and Nitinol, and starting to learn more and more about it. So what I hope to tell you and give to you guys today is just a better understanding of the use of Nitinol in medical devices, and to kind of demystify, in a sense, what shape memory and what superelasticity are, and how we can use those to our advantages, and in fact that the term shape memory and superelasticity are actually the same phenomenon linked through thermodynamics. So today I'm going to talk about the history, just a little about how Nitinol got started, how Nitinol works, some of its engineering aspects, and where we see it today in use. So to begin, we have two distinct effects. We have shape memory and superelasticity. What shape memory basically is we take this coiled wire we see pictured here, apply heat to it, and then it changes to the word hot. The wire rewraps itself around. So we can basically apply a thermal stimulus to it, and it makes a shape. Then we can cool it down again, bend it back into that wire jumble, heat it up again, and it comes back to this hot shape or hot picture you see over here. For superelasticity, what we find in Nitinol is we can, with the stent pictured in this catheter over here, is we can crush it, deform it however we want to, and somehow it's able to spring back to shape. So, in fact, these two are linked, and I'll talk about that a little bit more, but to delve right into the history of Nitinol. Nitinol actually is an acronym. It stands for Nickel Titanium Naval Ordnance Laboratory. It was discovered in 1959 by William Buehler, working at the Naval Ordnance Laboratory, as he was trying to figure out different combinations of alloys for naval ordnance purposes. When he stumbled upon combining nickel and other substrates, he came across a comparable 50-50% nickel-titanium mixture, and he got Nitinol. Pictured over here is Frederick E. Wang, who joined Buehler's group later on to do some of the first fundamental development work of Nitinol. And in the picture you see here, you see Buehler holding a device with some batteries and a piece of Nitinol wire in between it to test the Nitinol's electrical resistivity. And you can see pictured over here, Frederick Wang has a Nitinol perpetual motion engine. So, being this new phenomenon of having this material that you could heat back to shape, people had the first inclination of trying to use these things in perpetual motion engines. So the idea would be you have the cold wire, you apply heat to it, and it would constantly go. However, they found that the thermal efficiencies of this were pretty poor. And so actually the first real application of Nitinol in industry at all was with the Raychem CryoFit coupler. It was a device that they would use to easily fasten airplane hoses together. And so it used the shape memory property of where they would crimp it at a cold temperature, cool it down, blow the two tubes together, expand it, and then let it go. It didn't see a stress or it didn't see anything else. It just had to crimp the two tubes together. Where we actually first saw Nitinol in terms of use in medical devices was with what we consider to be the father of interventional radiology, which was Dr. Charles Daughters. In the mid-1960s, when physicians were looking more into preventing atherosclerosis or treating it, Dr. Daughters had the idea of taking a Nitinol wire, coiling it up, inserting it to a blood vessel, and then running a warm saline solution through it to expand the wire and open the vessel. So this was kind of the first beginnings of the use in Nitinol in the medical industry. Even though given its crude wire design, it was kind of shelved for a while and then later brought back up in the mid-80s and early 90s. And now that brings us to kind of where we are today with Nitinol and medical device development. Pictured over here, we have the Cordis Incraft, which is an abdominal aortic aneurysm device. You can see that we've gone from that simple wire used to open arteries to a more complex device with a glass on it to prevent aneurysms. And pictured over here we have the Medtronic core valve, which is a transcatheter aortic heart valve. So you can see we've come a long way from thinking about Nitinol being used for perpetual motion engines to all the way to more complex medical devices. So now I'm going to talk to you about how Nitinol fundamentally works. We can get a better understanding of how we can use that to our advantages in the engineering world. So to start off, if you don't have very much of a material science background, I want you to kind of think of it this way. Materials have phases, just like matter has phases. So water can exist as a gas, liquid, or a solid, such as ice. And what we want to take from that is materials can exist this way as well. And so nitinol has different phases to it. And I'm going to start with what's called the high temperature phase of nitinol, or the austenite phase. When we look at the crystal structure of the austenite phase, it's an equiatomic structure. It's a simple cubic. If you imagine that the red atoms at the center are nickel atoms, and for every blue atom, a titanium atom, there is for every nickel a titanium atom. It's an ordered structure. You can see that this ordered structure produces a fine subgrain network. What this picture is of an optical transmission electron microscopy. And you can see the scale is very small, meaning it has fine subgrains due to its ordering. All the angles in the crystal structure are at roughly 90 degrees. What this produces is it produces an interesting stress strain curve. A little lagging behind on the computer. I'm not seeing the image yet. Just keep going. Okay. So there we go. So the ordered crystal structure produces a stress strain curve that is similar to most other metals. The interesting thing about the austenitic stress strain curve for nitinol is that it has a very actually low elastic modulus compared to similar steels that operate in this behavior where they have very little strain until yielding. Nitinol has a very low yield point and then quite long work hardening rate. So the key thing I want you to take away from this slide is that this is a stress strain curve for non-transforming austenite. It's an austenite. It's a nitinol that's basically not able to go through a phase transformation in a sense. It stays austenite throughout the test. And this graph plays a key important role later on when we talk about the different operation temperatures that we can put nitinol through. So the other phase I want to talk about for nitinol is the Martensite phase, which is the low temperature phase. It's a uniquely different crystal structure than austenite. When you look at the optical TEM picture down here, you see it at a much larger scale, and it has these raised ridges, which are actually lenticular patterns highlighting twinning. So twinning is the main mechanism for which the shape memory and superelastic effects occur. And another reason why we're able to accommodate this phase, this low temperature phase, is that there's 24 different variants of Martensite in nitinol. Now, when we look at the crystal structure over here, we can see it's a little bit more complex and a little bit less symmetrical than that V2 structure we saw with austenite. So again, highlighting the differences between the two, austenite is more ordered, which produces a finer grain network. Martensite has less symmetry and produces the raised ledges or reticular ledges for twinning. And the key point of that is they're two distinctly different phases with two distinctly different sets of properties as well. So when we look at the different sets of properties that austenite versus Martensite have, we can see that there's no difference in density. However, there's a difference in electroresistivity, thermal expansion, thermal conductivity, and even magnetic supersusceptibility. The key thing between the two phases is that there's no change in density. This is important for exhibiting the superelastic and shape memory effect. The fact that there is no change in density highlights some of the inner workings of the twinning process, which I'll describe next. So twinning is important for the shape memory and the superelastic effect. So if we look at this crystal structure at the top, we see, if we imagine that for every large black atom is a nickel atom and for every small black atom is a titanium atom, we see this is a 2D projection. So we're looking down on the crystal structure. Okay, we see we're in the austenite phase. And then when we move from austenite to Martensite, we create this zigzag structure in the bottom. And if we literally just take a line and draw it through the middle over here, we see that what we create is a mirror image plane, or in crystallography, a twin plane. Basically, the top portion of this structure is a mirror image of that on the bottom. And so when you have pockets of martensite nucleate within the austenite structure, you create twin planes. So as these new structures are forming all over and combining together, they'll crash together and form a mirror plane between the two. So in other words, you can think of your hands as being twins to each other. If you draw a plane between them, your hands are mirror images of each other. So the important part of twinning in nitinol is that it creates these low energy boundaries that are parallel to the twin plane, pictured again in this 2D projection here. You can see that these low energy boundaries parallel to the twin plane are very mobile, and so when stress is applied to them, they accommodate it very well instead of some of the conventional things you think of as slip and more dislocations forming. So in effect, when the stress is applied, the boundaries are slightly shear in this example of a 2D projection, and allows for an easy accommodation of stress and not actually breaking material. So we can change nitinol simply by changing its temperature. And the thing we look into is that the material doesn't actually, the bulk material doesn't change in front of us. When we put it in a cold solution, it doesn't bend. It stays that same raw piece of metal. And that happens because of two mechanisms. That happens because of lattice deformation and lattice invariant shear. Because if we didn't have those two mechanisms working together, if we dumped that piece of nitinol in a cold solution, we'd see it jumble up and bumble together. But in fact, it stays that raw, long bar of nitinol. So what lattice deformation basically is it's small atomic shuffles to move from one crystal structure to the next. Now, again, if that was the only part of the transformation within nitinol, we would see one structure change shape in front of our eyes as we cooled it. But the other part of this transformation is the lattice invariant shear. And the two mechanisms that typically happens within structures is with slip and twinning. So the lattice invariant shear allows these new pockets of material of austenite to populate within the austenite matrix. It allows the material to fit into shape. With slip, you have basically the new structure being crammed into the other one, and you have dislocations forming, and in a sense, you're deforming the material, or possibly deforming the material. With the increasing martensite within nitinol, you have increasing strain energy as you're moving from one crystal structure to the next, which plays an important role in nitinol's thermodynamics. So as you have increasing strain energy from the transformation over, the increasing strain energy causes that transformation to happen over a range of temperatures. And we don't actually go from complete austenite to martensite right away or the other way around. We go through a series of stages where there's more volume fractions of martensite being populated when we look at either the heating curve or the cooling curve, when we're going from hot to cold and cold to hot. So this graph down here is a graph of volume fraction of martensite to temperature. And if we focus on first the cooling curve pictured in red, when we go from an austenite to a martensite, we see it happens over a range of temperatures, and we have what's called the martensite start temperature, which is where we begin to see pockets of martensite form and the volume fraction of martensite increase. And then you see we reach a final point where we have complete 100% martensite in the material, which is called the martensite finish temperature. And the same thing can be said of the heating curve when we go from an austenite start temperature, so still we're at 0% of volume fraction of martensite, and as we gradually heat the material back up, we go to 100% austenite, or austenite finish temperature. So again, if we go back to that analogy of different matters operating in different phases, when we take a piece of ice and we heat it back up to water, we're going through what's called a first order phase transformation. And that's typically seen in nitinol as well. So what this is exhibiting here is called a differential scanning calorimetry curve. For industry, this is what we mainly use when we examine bulk ingot or raw material. What it basically says is as we change the temperature of a sample, we can monitor the heat flow in and out of that sample. This gives you the most accurate transformation temperature of your material, but it's not really, it doesn't say much about how your device will function at its so-called finished temperature. It gives you the finished temperature of a bulk ingot, but it doesn't really tell you that well how your device is performing in its AF temperature. But if you see at the curve here, we go on the cooling curve. When we transform from austenite to martensite, we have heat release, heat flow out of the system, and we can monitor the same on this curve. When we go from martensite to austenite, we have heat absorption. So we understand Nitinol thermodynamics. We understand what happens with Nitinol stress strain curve when it's non-transforming austenite. And we understand how the martensite pockets nucleate within the austenite. So what then happens when we apply a stress to just a martensitic piece of nitinol? When we apply stress to a martensitic piece of nitinol, we see a phenomenon called detwinning of the martensite. So remember I said before with those twin boundaries forming? When we apply a stress to those, the boundaries parallel to that twin plane are very mobile. As soon as the stress applied in that 2D projection, it's allowed to shear past one another to accommodate that stress very easily. So when we look at a typical stress strain curve for martensite, we see that as soon as we have loading, we have a small elastic pulling of the martensite, and then we have detwinning. We reach this plateau where literally all the twins are taken from one state to the next lowest energy state to accommodate that stress. Once we've finished detwinning, we go to an elastic pulling of the martensite until final yielding. And this plays an important role as well with superelasticity. So you can see in this projection of this crystal structure over here, we go from the twin martensite form, and as you can see, we apply slight shearing in this direction to move to this structure. So if we combine our understanding of nitinol thermodynamics, moving from one crystal structure to the other, we get what's called the shape memory effect. So when we look at a piece of nitinol material and that exhibits the shape memory effect, we start with a nitinol material in the austenite phase, high temperature phase. We cool it. Cooling creates the twin martensite. We apply stress to it. The martensite accommodates that stress by forming detwinned martensite. And then we finally, when we apply heat to it, we form it back into the ordered austenite crystal structure. And you can see that in a piece of material again when you take a red bar being the hot material, cool it to blue, cold, deform it, and heat it back up, it comes back to shape. So that's the shape memory effect. However, we also heard that nitinol exhibits superelasticity. Basically, you can crush it and it comes back to shape pretty easily with enough applied force. So this occurs through, I want you to understand that this occurs through the same mechanisms that shape memory is occurring through. The only difference is it's an applied stress at a warm temperature. So what happens is you start with the ordered austenite cubic structure over here, with every large black atom being nickel and every small blue atom being titanium. And as soon as you're applying the stress, you have slight shearing movements. And what's happening is you are stress-inducing martensite in the material. So you're still going through the same steps. When you go through the shape memory effect, you cool it down, it becomes twin martensite. You apply the stress, it becomes detwin martensite. The same is happening with superelasticity. When you apply the stress, it's twinning, but as soon as it's twinning, it's tending to detwin to accommodate that stress. And so when we look at the stress strain curve, we see that. We have the initial up to about 1% elastic pulling of general austenite, and then we reach a plateau, just like we saw in that martensite phase. We reach a plateau because we are stress-inducing martensite, we are stress-inducing a phase transformation. Finally, we reach a peak where we can no longer stress-induce phase transformation, and we have elastic pulling of that detwin martensite. So it's going through the same mechanisms, okay? And the phenomenon is really linked through thermodynamics. And just to illustrate in the picture over here, this is a sample that was pulled at 60 degrees Celsius, and that has a AF finish of 0 degrees Celsius, meaning that at 0 degrees Celsius, a raw piece of material has 100% austenite, and then it's loaded in a tensile test. So the phenomenon that they're linked through is through the Clausius-Clapeyron equation. So basically, if you go back to that matter analogy, what happens when you take a piece of ice and just apply a pressure to it? You can actually make it turn into water by keeping it at a constant temperature, by just applying that pressure. And so the Clausius-Clapeyron equation says the same thing. And in this terms, our pressure is just a stress. And so we have a certain stress rate, which was related to a heat flow out of the system and an initial temperature of the two phases and a strain rate. And so you can see too that with the previous curve on this axis, I had a volume fraction of Martensite, and I saw the temperature. The curves look the same, and that's because they're linked through this. They're linked through the fact that you can induce a phase transformation by applying a pressure or a stress, just like you can induce a phase transformation just by applying through a temperature. So when we kind of combine that all together, we fundamentally understand how nitinol is behaving in a crystal structure. Then we can use that in our advantage to, I say, design a stent, design the certain characteristics and properties of the stent we want. So again, we go back to that typical stress strain curve for a sample that has an austenite finish of 0 degrees Celsius and a test temperature of 60 degrees. Now, when we look at the type of material we want to choose, nitinol, it comes in basically two flavors according to the ASTM standard. It comes in accordance to Superelastic 508 or SM495. Superelastic 508 means it has 50.8 atomic % nickel, and SM495 means it's shape memory 49.5% nickel content. What that basically illustrates is this. So we see a phenomenon as well where, is everything okay? Technical? Okay. We see a phenomenon where that happens where you can change your AF temperature and you change your stress plateau. And that's actually happening based on our material properties. So when we have a higher percentage of nickel inside our nitinol matrix, we can actually lower our AF temperature. And in terms of a device, we can have a higher stress plateau, meaning you're going to have a stiffer stent. And in turn, when we put nickel out of the matrix, of a nitinol matrix, we can actually increase our AF, and we can actually have a lower stiffness for our stent. And you can see that in these typical flag nitinol curves over here. So the take-home message from this is the lower AF you have, the higher stress plateau you're going to have, which means the stiffer device you're going to have. And that, again, is controlled by the type of alloy you're using and how much nickel is inside your matrix. So, again, if we think of these being SE508 material, well, what really happens for how much nickel we're taking in and out of that material for that parent matrix? So when we look at this graph over here by Harrison et al., it basically says to us that when we look at it as a function of Martensite start temperature, the more nickel we have in our matrix, the more suppressed our Martensite start temperature is. And the less nickel we have in our matrix, the higher our Martensite start temperature is. Again, we can still think of this in terms of austenite start and finish temperatures as well. Again, you just have to think about which curve you're on. You have to think about if you're on the heating curve or the cooling curve. So you can see here that if we're actually on the cooling curve, it means that you're gonna start to see Martensite at higher temperatures. And the same thing will happen with the heating curve. Basically means you're going to start to see austenite at a higher temperature as well. So we can use this to our advantage in changing the slight material properties to give us better stiffness, better performance, and better strength in our device. So the way this works is we go back and we'll look at the phase diagram for nitinol. And we can see that nitinol, this is a typical phase diagram, so we have atomic percent nickel on one axis, temperature on the other. And we can see that nitinol is very only stable across a certain range of nickel percentage and temperatures. It's very intolerant of substitutional defects. Deviating slightly gives us these nickel-rich precipitates, this Ni3Ti or this Ni3Ti2. This notation is just what some of the papers say. They switch the titanium and nickel around, but it's one and the same. So you can think of moving these precipitates in and out of your nitinol matrix. That'll change your transformation temperature based on the graph we saw before. So obviously, if we put a little bit more nickel in, we're going to lower our AF or our Martensite start temperature, and if we let nickel out, we're going to raise our Martensite start temperature and raise our Austenite finish temperature. So we can do this by different types of heat treatment. But before I go into that, what I want to stress is that nitinol can only operate over a certain range of temperatures, and that you really have to pay attention to the AF of your device. It's your most important material criteria. If we look at a piece of nitinol that's pull tested over a range of temperatures, we see this. When we start at negative 100 degrees Celsius, we see a typical Martensitic stress strain curve. We move to negative 50, we see the plateau raise a little bit, but we still see the typical Martensitic stress strain curve. Finally, when we reach 0 degrees Celsius, we see a superelastic curve with a flag that has the hysteresis. And again, this sample it has an AF of 0 degrees Celsius. And we see as we raise the temperature more and more, we're raising our stress plateau until a point where, again, that non-transforming austenite graph comes back into play. We see it reaches a point where we can no longer stress-induce a phase transformation, a stress-induced Martensite in the material. And this is called the Martensite deformation temperature. Summing all of this together creates what's called the nitinol operating range, or its superelastic window. What it basically says is that nitinol can only operate over a certain range of temperatures. And this is important to us when we think of a device because we want a device to be stiff enough. However, if we think about post-processing techniques, either sterilization, that plays a key role too. Typical EO sterilization maybe happens around 60 degrees Celsius. And when you look at this graph over here, at 60 degrees C, you might have a little bit less than 1% permanent set in your material. Again, this is an austenite finish temperature of 0 degrees Celsius. We look on the graph over here, we have high permanent set at these lower temperatures because we know we're operating in our Martensite phase. Once we hit 0, we have almost no permanent set because we're operating in our superelastic phase. But if you think about it, based on those earlier curves, by shifting your AF, you can shift how stiff your device is. When you shift your AF, you also shift this window. So if you imagine a customer says, okay, I want an AF of maybe minus 20 degrees because I want a super stiff stent. You're going to shift that window down, and you might actually hurt your device when you go to sterilize it, which isn't good. So you're going to have permanent set in your device when you go to sterilize it. So those are things you have to keep in mind, that nitinol really only operates superelastically over a given range of temperatures. And you can determine that just by testing and figuring that out yourself. Again, superelastic window. And so on the other the other thing to consider too, again, is that when you increase your test temperature based on your AF, again, AF is 0 degrees Celsius, you have a linear relationship between your upper stress plateau and your lower stress plateau. And again, at the Martensite deformation temperature, you see that the ultimate tensile strength of your material doesn't really change until you reach this point where we can see that the upper plateau stress is meeting it, which is indicative of our Martensite deformation temperature. So you have to keep in mind that when you reach these high temperatures like that, you have to watch out for how much permanent set is going into your material and how much you're destroying it. So again, we want to change things to our advantage. We can heat treat or shape set our devices. So when we do that, we can get detrimental effects in our ultimate tensile strength of our material. It's basically a trade-off. So higher temperatures will give you a better shape. However, the better shape will have a detriment in the ultimate tensile strength of the material. So at 600 degrees Celsius shape set time is going to give you a good shape. However, the more time you do it, it's going to seriously decrease the ultimate tensile strength of your material. And you can also think of the ultimate tensile strength going in parallel with your upper plateau stress, meaning that if you're decreasing your ultimate tensile strength, you're also going to decrease your upper plateau stress and decrease the performance of your device. So really picking your heat treat time to move those nickel-rich precipitates in and out of your matrix to control the properties you want is a trade-off. So you really got to pick a time and temperature that's not going to detriment this too much. So these are things you got to keep in mind when you process your material. So to do that, when we want to pick the correct time and temperature, we look at this graph over here, which is a function of our AF, taken from a sample that initially starts at 0 degrees Celsius and moves in a time fashion over here. We can see that with the higher temperatures we go and the lower times, we're significantly dropping our AF. But again, if we look at the path graph, we're detrimenting our ultimate tensile strength. So we have the point of this graph is we need to pick a balance. So if you want something where you want to slightly drop your AF, but you want to keep good material properties, you might pick something that's just slightly over 500 degrees Celsius, such as 525 in the blue circles over here. You see, we all start at this point, or sorry, we start here. We initially drop, and then we reach a point where we plateau up. So again, this is just things you need to keep in mind when you shape set and when you play around with heat treatment times and temperatures for your nitinol material. So functioning over here, as probably some of you are familiar with, is a TTT diagram. It's a time, temperature, and transformation. So this is done specifically for the device or material at an AF of 0 degrees Celsius. We have temperature and time on one axis. And the point of this graph is, okay, maybe I have a device and I want to make it less stiff and raise my F temperature. Okay, so I want to raise it to 20 degrees. It'll make it a little bit flimsy, but when it reaches body temperature of 37, it should operate accordingly. So what time and temperature do I really need to choose? Well, one of the options you have is you can choose maybe around 450 degrees Celsius for about a minute. However, the problem with that is you can see you're on a steep part of this curve. So your process is going to have a lot of variability if you think about it. You're going to take a piece of material, you're going to heat treat it, it's going to be warm, and you pull it out of the bath or whatever you're using to shape set it. It's going to cool off a little bit, and then it's going to quench. So it's actually experiencing a range of temperatures. So it's really hard to control that like 450 degrees Celsius mark for that minute. So taking this point to operate on your TTT diagram to change your AF or shape set your material is not the best thing. You want to reach a region over here on a plateau where basically you're not going to see much of a difference between 8 minutes and 10 minutes in your processing time, and you're going to get that AF temperature that you want. So this part of the curve is more stable to your processing. So what it produces is it produces more repeatability in your processes and in your devices. So when I talked before about the differential scanning calorimetry graph and the heat flow in and out of the material, it's really not good for testing the functionality of your device. When we test the functionality of the device, we look at the ASTM standard F2082-06, which says we need to do bend-free recovery of the nitinol material. Bend-free recovery is just using nitinol's shape memory aspect. You cool it, you let it deform, and then you heat it back up. But when you're watching it heat back up, you usually attach it to a weight. So say you've bent it and it's got the weight pressing down on it. As it starts to heat back up, it's going to push that weight, and you're going to be able to get a graph of a length versus temperature. And then you're going to see when there's a drop-off between your length and temperature, and you're going to be able to draw tangent lines to figure out where your Austenite finish temperature is. Now, the ASTM standard says that for wire, you need about 2% strain in the material. What we care about most is how functional your device is going to be. So when you take a stent, the point of it is you crush it, cool it down, put the weight on it, let it heat back up, and once it heats back up to its final configuration, that's what you care about the Austenite finish temperature be. You care about when the device is fully recovered to the point where it can operate. So now that we understand, a lot about the different treatment times and different testing methods we can do to figure out how we want Nitinol to operate and how it is operating, one of the most important things in the medical device industry is how to make it biocompatible. Nickel is very poisonous to the human body, and one way we can do this is through chemically processing the surface. And we do that through chem polish and electropolish. The beauty of Nitinol is it can have having a thin titanium dioxide layer is what makes it biocompatible. Usually the layer is between 50 and 80 angstroms thick, but it's that layer that allows your device to function within the human body. So using these two different processes, we can get a better surface finish. So the picture here is of a device that was implanted with a thick oxide coating and that hadn't been surface treated, and you can see how much it's corroded inside the human body. Here we have a wire that was electropolished. You can see the difference between the two after explant. So finally, pulling that all together, where do we see Nitinol operate in our everyday lives? So probably what you're most familiar with Nitinol, and all of you have had that experience with, is with dental arch wire. So they found out in the 1970s when they were putting braces on that Nitinol arch wire could last a lot better and you had faster treatment times. And that's because of Nitinol's superior strain accommodation techniques. So that's typically why we see Nitinol arch wire used in orthodontic application, is because it's a good strain accommodator. And the point of braces is you need teeth to move. So the perfect application of that would be with Nitinol arch wire. Where we see other applications of Nitinol today, I'm sure many of you probably had this in the past, but how many of you had bendable eyeglass frames? That's Nitinol, believe it or not. So that was a big phenomenon we saw with eyeglass frames. However, as what we've learned today, obviously you couldn't work very well in the very cold because there's only a certain range of temperatures at which Nitinol can perform to its best capabilities. Where we see it being used mainly today is with inferior vena cava filters. Pictured here, this is one of the first Nitinol medical device implants. It's called the Simon Nitinol filter. It's used to prevent against pulmonary embolism. And here we have the Cordis Smart Stent, one of the more popular and dominant market shares for the endovascular stent market. The reason we use Nitinol in the endovascular stent market is because it needs to be flexible. We're not putting a stent in the heart where it's not seeing much movement. We're putting this stent in your leg or the back of your leg in your superficial femoral artery. And it's really got to be able to accommodate great strains and pop that vessel open to create blood flow. So that's why we see Nitinol being used in the peripheral stent market. Finally, some of the take-home messages I want you guys to have from the talk is that superelasticity and shape memory are the same. Just think of the analogy as matter. You can change matter through temperature, and you can change matter through changing pressure as well, and that pressure is a stress, just like Nitinol shape memory and superelasticity. AF dictates the function of your device. It basically says how stiff your device is going to be and how it can operate. You have a trade-off between processing and function. If you want a stiffer device slightly, you're going to have to pick a correct processing time that's not going to hurt your upper plateau stress or your ultimate tensile strength. Nitinol can be very biocompatible, and it's the best material on the planet, in a sense, to accommodate strain-based applications. And finally, even though it has a non-linear elastic modulus, don't be afraid to use Nitinol in your medical devices. Thank you.
And I guess we'll open the floor to questions here in the room. I don't know also if there are any of the virtual attendees who might have questions as well. Anybody in the room we can take.
All right. What was that number? The shape memory. We got Superelastic 508.
Oh, and SM495.
Grain size so you can associate with it?
Grain size depends highly on the thermomechanical processing. So to create like the shape memory and superelastic effects and all that, you actually have to cold work it enough to put in dislocations. So the grain size really depends on what material you're picking and what applications of it. So I can go into more detail a little bit later on about that, about which materials you're looking at would have finer grains and things like that, and how that affects. I mean, it doesn't. It's important, but in terms of looking at a device perspective, we don't really typically worry about it as much. There's this whole debate on whether you buy material from one customer or another, and they have a finer grain or more carbon or less carbon in the material as it operates better. But really, from a device standpoint, it's not as significant.
Are there any virtual questions?
The time you mentioned Charles' daughter. So using nitinol couplings for aircraft, for coupling wires.
Charles' daughter was using nitinol for opening arteries.
Right.
Yeah.
That time, what application was it and outside of it?
I mean, they've got on perpetual motion engines for a while, and they're still trying to do that. Actuators, springs, electrical resistivity. It's good for that. However, you have complicating things like, depending on what temperature you're operating on for the electrical resistivity, as you saw, Martensite can be different than Austenite. And actually, I didn't talk about this a lot, but there's another competing version of Martensite in nitinol called R-phase. And so electrical resistivity has problems with that because you compete with that. But those are some other applications. Springs, actuators, eyeglass frames, toys. There's been toys that have used little bits of nitinol for strain things.
When the material first came out, it was extremely expensive.
Mm-hmm.
And over time, costs have gone down. Why is that? What was done? What was the cost?
I think it's a combination of better processing techniques and better ways to melt material and to draw it and things like that. Back in the early days, I mean, I don't think they had a better understanding of what was going on with the crystal structure, and once they started to understand that more, they could use that to their advantage during the melt and during the cold work and things like that, to better control and to make it cheaper for the consumer. Mm-hmm.
So when you have to check for stents and see that they're radio opaque, is there anything naturally radio opaque, or do you have to add something in it?
That's a good question. I didn't touch as much on that subject, but nitinol itself is not very radio opaque. You actually have to attach platinum or tantalum and sometimes gold marker bands to it to have it show up better under fluoroscopy.
And is that something you have to special order from the raw material supplier, or is it post-process?
It's usually a post-process. So in typical terms, like when you laser cut a stent, you usually cut out little eyelets or windows, and you'll either stamp a tantalum or platinum coin into that window. And the big concern that you have with that is now you have, so corrosion, right, with the biocompatibility surface. The scary thing you kind of play with when you have radiopaque markers like that is you have galvanic corrosion now because you have two dissimilar metals on your material.
I don't know if there are any other questions or if there's been any last-minute entries in the chat box. But we'll thank Louis for his time giving this talk. And I'll just also make a quick pitch for our event next month. We're going to have another webinar series. We're going to continue with the topic regarding the new patent reform. And a licensing associate from North Carolina State is going to give his view on what implications will be for smaller developing companies, including those in the medical device sector. So thank you for attending and joining us either on site or virtually. And if you have any, if you're interested in registering, you can find this also on the hanteltech.eventbrite.com, or also email us at webinar@ hanteltech.com for any suggestions or other topics that you'd like to answer. Thank you.
Is it laggy on the laptop?